tolerate, encourage criticism by the pilots, which is really unique. For example, we have a process in the company. It's very acceptable that you don't write a fully detailed flight report. But immediately after the flight, the first thing that any Dassault pilot would do is write a small sentence, even, okay, the flight is good or anything works well. But if he has something that if he feels he doesn't like, he would say it. And where does that statement go? Directly on the top of the pile of mail of the top management of the company, perhaps 5 or 10 people in the company. And immediately, if you write that something is wrong, be sure that they are going to call you back in the day after and try to ask you more questions about it. But on the other hand, so the pilot opinion is very important to the company. The engineers are ready and trained, and I have immense respect for them. They are ready to accept the criticism. And, but on the same time, it gives to the pilot a very, very big responsibility. You have to be sure that, not that you are wrong or right in your judgment, but that at least you do not down-perform in your judgment. That means you do not, you try to be as good as you can all the time, and it's a very difficult task. But this ability to accept criticism, to have a way of reporting directly with short, real short sentences, statement, is to me very important. It was a dream organization also because everybody in test community at that time, it's less and less true, and I am a little bit desperate about this, had respect for the work of the other. That means we knew the crew chief of the prototype or of the aircraft. Each aircraft in test was assigned to a crew chief, and those people are very, very knowledgeable. They knew everything. They were able to dismantle the aircraft at night and make it flight the other day. So they know a lot about what you fly. The flight test engineer are really bright individuals. They are really the link between the design office and the pilot and the test team, and the engineers in the design office are really, top of the art people, especially in the domain of flight control system, etc.
Patrick, that was excellent, and I think you gave us a very important perspective on the very key relationship that has to exist between the flight test team, particularly the test pilot, and the larger organization. And unfortunately, we are, I think, a little pressed for time, and at this point, I think we'll thank you very much for that presentation, which was very, very informative to us. And we'll move on then to our final speaker in this morning's panel. Stieg represents the Saab firm. Saab, of course, if you take a look at the development of post-World War II aviation, Saab has had a string of extraordinarily well thought out airplanes, certainly going back to the days of the J-21 immediately after World War II. The J-29, the so-called Tunnan, which was a very advanced little jet airplane for its day, the J-35 Draken, a notable double delta airplane onto the Viggen, the J-37, and now, of course, We see Saab out there right in front again with the Gripen, and he will be talking to us about experiences and his views on flight testing given his experience with the Gripen.
Thank you, Dick. It's a pleasure for me to get this opportunity to tell you a little bit about an aircraft that maybe is not so well known here in the States, the Saab 39 Gripen. Actually, we brought two Gripens over last week to Andrews Air Force Base. They were supposed to participate in the AFA event and in the air show that would be there on last Thursday. But you all know what happened on that day. The Hurricane Isabel came, and nowadays that I am involved in marketing, I always get suspicious when that someone of our competitors lie behind this, but I don't know.
That was a cunning plan from our weather control branch.
Can I have the first slide, please? Yeah, this is the Saab 39 Gripen, the first prototype, and this photo was taken just after the first takeoff, first flight, which I did in 9th of December 1988. 1988, so it's not so long ago. I guess I held my breath at this point of the flight, but it all went well, and I will tell you more about it shortly. The aircraft is a multi-role fighter, fairly lightweight in this configuration, something like 9 tons or 18,000 pounds. Well, we flew in December, which the first time, which of course is a challenge in Sweden with the weather, but we had luck. You see that it was a good day for flying, no clouds. You can't see it, but there was almost no wind. It was cold for the spectators. There were a lot of people out looking. Prior to this, we had, of course, done a lot of ground testing. We had done high-speed taxi tests. My colleague Arne Lindholm, who is out here, did it together with me. We took the aircraft up to a speed where we could lift the nose wheel and get a feel for the response, the pitch response. But we had only 5 seconds of evaluation time because the runway at Saab is only 7,500 feet. So after 5 seconds, we had to throttle back and start braking. But anyhow, we got to feel what it was like, and we were confident. And after these tests, we got approval to go ahead and fly it. So back to the first flight then. Immediately after I got airborne here, I noticed that the aircraft was too sensitive in roll. It was exactly as the first time you flew an aircraft with a boosted aileron. If you remember, I did that with in the Tunnan, the flying barrel. It was my, sorry. 1, 2, 1, 2, can you see me? These things. Must be something wrong with my ear. Well, anyhow, that was the only thing I didn't recognize from the simulator. Otherwise, the airplane flew like the simulator, which gave me great confidence. The reason that I hadn't seen this behavior in the simulator was probably because we had a very simple simulator. Fixed base, no motion, a fairly small visual, more or less a normal TV screen. And that screen was too small to actually tell the behavior of the aircraft laterally. But otherwise, during the first flight, things went as expected. Maybe I had a little more caution, lights coming on and warnings and honking than I had expected, but of course that is natural. First time all the systems come up in the air, they want to tell you that they are there, and they are not fine-tuned, the warning levels. So had a lot of those. Worst of all was the fuel system. And I'm sorry to say, Patrick, it's a French fuel system. But thanks to the people in the telemetry center, the experts, flight test engineers, who was there following the flight in real time, we could sort all these things out, and I could continue the flight almost as planned. The only thing I didn't do was to light up the afterburner, because my fuel gauge, as I said, wasn't steady, so something funny was going on in the fuel system. But otherwise, I did the flight. It lasted for 51 minutes, pretty much in the middle of the envelope, doing some handling qualities assessment and functional check of most of the systems on board. Went up to 20,000 feet something, and Mach 0.7. So after that first flight, we had a pretty good envelope opened. Someone has said that the main purpose of a first flight is to make a successful landing. And, and that I did after these 51 minutes, and we were all happy. Of course, there is much more to tell if we had time to go into details, but there are some lessons learned. The first flight was very successful. Then we had failures after that, but we also saw the opportunities behind the ice. So we have solved those problems we had related to the flight control system. We have come up with solutions, and we have now an aircraft that flies wonderfully. It's really a pilot's aircraft, very responsive and quick. So quickly, some lessons learned. The simulator, I would have wished that we have had a better simulator, maybe one with motion and a larger visual thing. We would have done more in-flight simulation. We did some with Kalsman, but again, as we have heard many times during these days, the program, the milestones, the economy, and those things, it put limitations, and sometimes it was decided that we want to save time, we want to save money, we don't do that. And it got me to think about that Brazilian oil rig. It wasn't that worse, that bad in our case, but similar things happened. So you have to fight the management, the program management, and those who have the budget. And we have heard that before, haven't we? Well, Dick, thank you.
Thank you very much, Stig. There's been some very interesting themes here this morning. One I think that has come through loud and clear is that we need to get better in the ability to match prediction and simulation with flight test. That's no surprise. You know, it mirrors what we always had in the aerodynamic world, where you had always the difficulty of reconciling wind tunnel results and wind tunnel testing with testing from full flight vehicles. And the second is we need really to work in improving the relationship between the flight test community and program managers and people whose bottom line is governed by the dollar symbol or kroner or whatever. You know, this is clearly something that's been a continuing problem, and obviously it's going to be something in the future. Now, I would ask that if you have questions of these gentlemen, they'll certainly be available after this presentation. We've had an extraordinary morning. I'd like you all to show our appreciation to these notable pioneers. Gentlemen, thank you very much indeed.
Thank you.
For this operation. The pilots never landed the Mosquito on the carrier. They'd been given an easy airplane to land just to give them some confidence, and on the day it was all or nothing at all for them. And they were pretty well ready to undertake the operation when the atom bomb was dropped at Hiroshima. So it was all called off. But that was the world's first deck landing of an operational twin-engined aircraft. And there was one problem, I have to tell you, we never solved, and that was trying to land the aircraft back if it had an engine failure. There was no way that we could do anything in that respect, because this aircraft couldn't be held under control beyond 170 miles an hour. So below that, you were going to yaw into a roll. So the object was achieved, and the end result was that out of it all, although the operation wasn't carried out, we learned so many lessons that we produced what, in my opinion, is the finest piston-engined airplane I have ever flown. Could I have the next slide, please?
Sure.
That is the de Havilland Hornet, which is a little brother of the Mosquito, single-engined, very overpowered, and with handed props, so that you had no problem with swing on takeoff. And I'm doing the first landing of this on the very same day that the atom bomb again was dropped at Hiroshima. So it arrived too late for World War II, but it was a magnificent airplane. I used to do an aerobatic display on it with carrying one loop with both engines, then a loop with one engine, and then a loop with no engines. And the thing was, you had to be sure that at the end of this nonsense you could unfeather the thing. So, well, did you carry a spare fuse? No, sir, I carried a nail. And that way, if you put the nail in, something's going to go, but it isn't going to be the nail. You can bet your bottom dollar on that. Anyway, that's briefly the story of this particular operation called Operation Highball.
I think we've learned a lot about the character of naval aviation testing in the Royal Navy at that time, and also an awful lot about the character of our speaker, Eric Brown, a remarkable man. Would you please join me in showing our appreciation to him? The Hornet was a tremendous machine. The Royal Air Force operated it. In fact, they flew it in Malaya against communist insurgents in the 1950s. If memory serves me right, it was about a 487-mile-an-hour airplane, and one wishes that one had survived. It'd be interesting to see it at Reno. Our next speaker is Vice Admiral William Bowes, U.S. Navy retired, an SCTP fellow, TPS grad, 3 tours at Pax River, instructor at the school, chief engineer on many, many programs for the Navy, and he's going to speak to us about the evolution of carrier suitability testing from in the post-war era from 1945 to the present. Admiral?
Thank you very much. I'm really humbled to have been asked to talk to this august group. Just to give a show of how many other carrier suit pilots are out in the audience, why don't all the people who have been carrier suit pilots or are stand up? Okay, so if anyone has any questions that I know Kurt or I probably can't answer, there's probably an august group. I'm sure any one of the people out there could stand up or sit up here and give a very similar presentation to that which I'll talk about over the next few minutes.
Another way to look at this is an oral exam and they're here to question you.
Oh, okay. Well, if I talk long enough, there'll be no time for questions, so I'll just do a quick monologue here. But carrier suitability testing, I'll pick up from where Eric left off. Certainly, the United States learned so much from Great Britain with the steam catapult and the angled deck, and World War II certainly showed the power of marrying airplanes and ships. And after that time, 1949, the U.S. Navy started a department, Carrier Suitability Department. It continues to exist today, various changes to the name, but carrier suitability still is the handle most of them go by, although ship suitability, including dynamic interface for helicopters, V-22 is now part of that team at Pax River. The one thing that I think we have all learned about operating an airplane on a carrier, certainly been many great successes with the Doolittle rate of the B-25s, and Jim Flatley, who's not here to talk about bringing a C-130 aboard. In 1962, we brought a U-2 aboard. But the objective of carrier suitability for an airplane is to ensure an airplane can not just make a trip on and off or off, but to continually operate from a carrier in a carrier environment. And that means routine operations to land, take off, and be supported and armed and repaired, and live in that environment and make thousands of landings over its life, as our airplanes are doing every day. The techniques that one has to use is you can't start, although there have been some successes of taking an airplane on, and as Eric mentioned, you need to start and build an airplane pretty much from the ground up to be a carrier suitability airplane, to live within the design envelope, to fit on elevators and JBDs and on the Catapult, and be able to be adaptable for the arresting gear and the CATs that are on the ship. And so the role of carrier suitability testing has been a unique role that the Navy certainly has enjoyed over the years. And certainly when I graduated from test pilot school, shortly after Kurt and I served together at carrier suitability, as did several in the audience today. We ended up in carrier suitability having the distinct ability to test a part of the envelope that the contractor historically had not tested, although I'm pleased that now there's a lot more teaming, and as we go forward with Advanced Hawkeye, there's going to be a government industry team and be some contractors taking airplanes to boats, which hasn't happened. But a part of the domain of testing that was relegated to the Navy was the carrier suitability testing. And what is that? Certainly, it ends up being a marriage of the airplane to the ship, and that's all parts of the ship. It's not just testing the airplane, it's certainly making sure that it'll work right with the ship. And so as catapults evolve from the T-7 to the C-13 catapults that we have today, and now the EMALS catapult that's coming along, that's certainly a different environment, and there's a lot of testing to ensure that the airplane will operate safely there. The arresting gear changes that we've gone through, and then the various landing aids, from the old optical mirrors to Fresnel lenses to putting head-up displays to night vision lighting and drop lights and strobe lights and the whole night vision goggles, and day and night testing in the carrier environment has been a domain that those of us that have been privileged to be carriers or are carrier suit pilots today continue to go ahead and test. And then probably one of the more interesting evolutions is the Catapult minimum end airspeed testing, to ensure that you know what minimum airspeed you need to go launch the airplane off the Catapult so that it will not hit the water and not stall, but will safely fly away. And then obviously the structural testing to make sure that the airplane is going to handle the stresses imposed by the landing, both the vertical velocities as well as the catapult and arresting velocities and stresses that are placed on the airplane. And then with it, the host of aids that have come along from auto throttle development that was in its infancy when Kurt and I first started testing, where we would fly airplanes with what we called a diddle box. We would be changing the gains in flight as we'd fly along and come up with the optimum auto throttle to what we have today, that are vastly superior to what we were testing back in the 60s when I was involved in that end of the business, to automatic carrier landing development. First automatic carrier landing was made back in 1957 on Antietam with a combination radar altimeter and TACAN, to the kind of ACLS testing that Kurt and I were very heavily involved in back in the 60s with late spin 10s and then spin 42s and now spin 46, where it certainly does me, I feel that our system finally has worked with the men and women who've been flying our Hornets in combat and came back from Iraqi freedom, flying those 6- and 7-hour missions at night and coming back. The last thing you want to do is have to make a night landing by yourself, and turning it over to George, and George is pretty reliable now in the Hornet, and the number of automatic Mode 1 landings today has increased vastly over any period of time previously, where the technology certainly has developed to that point. Just to talk about one little anecdote, certainly the test pilot who I've always and continue to admire as the most capable of test pilots is the guy sitting on my right, Kurt Schroeder, who certainly taught me an awful lot and certainly got me started in many times the right directions. We did a lot of things they call shake, rattle, and rolls. And back in the 60s and continues today, every time there's a new weapons change, avionics change, something that's going to change the man-machine structural interface, you need to go verify that it'll operate safely in the arresting gear in the catapult environment. And sitting out there on the runway watching Kurt do some of his shake, rattle, and rolls or doing touch-and-go landings, I mean, the rule was when you turned downwind, you didn't want to scrape your wingtip on the runway. But yet you wanted to come as close as possible to go ahead and make anyone that was thinking of going beneath you on the turn very cautious of that. And so no one could do it as well as Kurt could. And those of us in carrier suit had a lot of familiarity with the landing gear down. I think most of the airplanes I flew for the 3 years I was there rarely raised the gear. You got very comfortable in PA configuration. My first carrier airplane to do a Catapult minimum manned airspeed testing, and I had the opportunity to do the structural demonstration of the airplane, was the remanufactured RA-5C with fillets and new engines in it. And then Kurt was the lead of the carrier det that we went aboard Independence together. There were RA-5Cs already in the fleet, but I'd never had an LSO wave me that I'd ever seen an RA-5 before, so I went down to Albany, flew in and figured I'll do a few touch-and-go landings just to get warmed up, and was doing typical Kurt Schroeder turn-down winds. I never scraped the runway with my wingtip, but I came fairly close, and wow, did I ever get... I got out of that airplane, immediately called up to the CO's office, and was summarily chewed out for not knowing how to fly this airplane. You know, it's a bomber. It originated as an A-12 or an A-5, and you're supposed to go straight ahead, 30-25 flaps, and then turn downwind. What happens if you would lose an engine turning downwind the way you were, which obviously I now learned that I was not flying properly. But next day we went out to the ship, and my first minimum end airspeed test, certainly you go through a lot of testing, identical things that you do today. The criteria that you use to determine a minimum certainly is minimum speed for acceptable flying qualities off the end, rotation limit, how much the airplane will sink before it gets to flying speed, or acceleration away from the carrier, A over G. You want to have at least 1 knot per second, or 0.04 A over G, to go ahead and determine what's an acceptable minimum. Today we have enough thrust in most of our airplanes that the A over G is no longer a parameter. It was not a concern, of course, for the Vigi, but I remember getting into the airplane and now wondering, or recollecting my paced flights when I was trying to determine what the minimum speed for acceptable flying qualities was. I figured I'd hire a chase airplane that I knew could fly as slow as I am. So we had an A1 with a boom on it. So the SPAD was flying with me, and I was 100 feet off the water, Chesapeake, doing an airspeed cal on this production instrumentation to make sure I knew what speed I was really at, and both burners slow as we could get, and he couldn't keep up with me. The Vigi standing on its 2 J79s is pretty impressive, so we kind of swagged that we thought we knew where it was. And I was getting in the airplane, praying that all my calculations were right. Kurt, the old father figures, puts his hand on my shoulder and says, "Hey, don't worry, it'll all work out all right." And so fortunately, we had a good starting point, and the first shot was 15 knots above where we thought the minimum would be. And the second one was, we obviously didn't, we had the conservatism there, but the second one we went right on down to well over 20 feet sink off the bow and right up to 28 units angle of attack in rudder shaker and full burn, and we just did our roosted tail in the water, and we did that one really smartly, and walked away with a nice success, and now we put 15 knots on top of that, and that's what the fleet uses. But the same techniques that we used then to go calculate what a minimum end airspeed test would be, or the speed, and the procedures that W over delta flying, the same things we did back in the 60s were probably done in the 50s and are still being done today by the wonderful carrier suit pilots that are at PAX today. So.
Great. Well, thanks very much, Admiral, for that presentation. Once again, I think we owe you a lot for your enunciation of that history and those personal stories. One housekeeping announcement before we get to our next speaker. With those panelists on the VSTOL panel, which is next, if you have not already been mic'd, make your way over to the corner there and be outfitted. Now, our final speaker on this panel, we've already heard a lot about him. Once again, no stranger to the society, a former society president, past president, SETP fellow, Kurt Schroeder, retired chief test pilot from Grumman, graduate of the University of Wisconsin, naval aviator, TPS grad, wide-ranging experience in fleet airplanes, F-4, the F-8, all the products of the so-called Grumman Iron Works. Vice Admiral John McCain once said the name Grumman on an airplane is like sterling on silver. They've had some pretty sterling test pilots at Grumman through the years that we can think of, and Kurt is right up there. Wide-ranging experience with all the Grumman products, F-14, A-6, EA-6B, OV-1, X-29 forward-swept wing. When I asked him before this presentation how he would characterize himself, he says, well, I've done damn near anything on carrier suitability. That includes automatic carrier landing development, catapult trials, carrier suitability structural demonstrations, work on taking the F-4 and turning it into the F-4K for the Royal Navy. So, Kurt, over to you.
Thank you, Dick. Just one quick comment. As Bill has mentioned, Bill and I have been friends for an awfully long time. In my career, I had the privilege of being the Grumman carrier suitability structural demonstration pilot for the F-14. And the requirements of what you're required to demonstrate on the airplane are dictated by Naval Air Systems Command. In his modesty, Bill didn't mention the fact that he used to command the Naval Air Systems Command, and despite our close friendship and my repeated requests, he's never shown me the cavern that exists somewhere in Naval Air Systems Command where all these diabolical, perverted people live that establish the requirements that you're required to demonstrate. So I thought I might just be a little bit more specific. One of the things that Bill has touched on briefly, and it's a test that's unique to carrier suitability testing, and that is the determination of the minimum catapult end airspeed for any particular airplane. The importance of this is because the flying speed that an airplane has when it comes off the catapult consists of what the catapult itself contributes, which is a finite value, and the balance of whatever that speed that needs to be made up is provided by the ship. So I think everyone can understand the lower that value can be provided by the ship, it has a significant impact on operational requirements for the carrier itself. So what the carrier suitability branch, and it's unique, everyone loves to do it, and that is to go out and actually do these trials. An airplane is determined how slow can you shoot it off a carrier is determined by one of three limitations. The first one Bill mentioned was the ability of the airplane to accelerate after it gets airborne. This was applicable to typically attack airplanes with heavy bomb loads, relatively low thrust to weight ratios that actually, once the airplane got off the cat, established a flyaway attitude. The combination of the parasite drag and the induced drag the airplane would be unable to accelerate. The next one is, Bill mentioned briefly too, is sink off the bow. When the airplane leaves the flight deck, most airplanes have to rotate to a flyaway attitude. So while they're rotating, the aircraft is settling. And each airplane is a little bit different, but the limitation that is normally used is they'll have somebody on the deck, laying literally on the deck and looking level with the deck, and if the airplane sinks out of his sight, then that determines that's as much sink as you're going to allow. And the third and final thing is what is called flying qualities, but really more accurately it's proximity to stall. In other words, that as the airplane gets off the deck, you don't exceed the stall angle of attack. One thing about carrier suitability when you're doing the catapult minimum end airspeed tests is most Navy airplanes are designed to be launched off the catapult essentially hands-free. In other words, you set a trim setting and the airplane goes off, and the characteristics, the behavior, the pitch rate is all predictable because it's all set before the catapult is fired. A notable exception to this was the F-4. The F-4 had a Q-bellows longitudinal flight control system in, and the pilot had to be in the loop. The pilot had to have the stick placed aft prior to the catapult launch. And this was demonstrated by a Marine aviator that if you don't do that, it will be a very short flight. the airplane will essentially go right in the water. So when the Navy airplane is at the more forward CGs, its minimum end airspeed is determined by sink off the bow. In other words, it takes a while for the airplane to rotate to the flyaway attitude. When the British they decided that they wanted to replace their Mosquitoes with F-4s. They came with a design to McDonnell to use a variation of the U.S. Navy F-4. The problem they had was the catapult capacity of their ships was not as great, so they needed a lower end airspeed capability. In the original design, in the existing design of the U.S. Navy F-4, there's a pneumatic extension of the nose strut of about 18 inches that puts the airplane at a higher angle of attack for the catapult launch so that it doesn't have to rotate as far, and it minimizes the amount that you have to rotate, but nevertheless, the minimum speed is still determined at the forward CGs by the sink off the bow. The British design, McDonnell added a second extension of the nose strut that was hydraulically powered that essentially doubled the extension that the U.S. Navy one had. This would then ensure that the airplane was closer to its flyaway attitude as it left the deck, and it was predicted to lower the minimum airspeed by as much as 20 knots. So we went out to the Coral Sea to do the shots, and as Bill kind of alluded to, is when you're doing these tests is basically they'll just shoot the airplane at slower and slower speeds. Initially, you reduce the speed by reducing the catapult contribution, but then as you get closer and closer to the actual number, they want repeatable catapult performance, and so they will then adjust the speed of the ship to give you the proper wind over the deck to give you the desired end airspeed. We worked our way down with the F-4K, and we were within 2 knots of the specification requirement. The launch went fine, everything was fine, trapped back aboard. The decision was made that we would fuel the airplane up and go for the actual minimum. We went up, everything looked the same. Obviously, they slowed the ship down that 2 knots, and on that launch, I did everything to get the optimum performance out of the airplane. The stick had to be held full aft until the airplane was airborne, and then observe the pitch rate of the airplane, and then come forward with the stick in order to establish the flyaway attitude. So I repeated this performance on the, quote, minimum shot, and much to my surprise is when I put the stick forward to establish the attitude, the airplane continued to rotate and went up and went into a stall. At 80 feet above the water, this was a little disconcerting, but fortunately, with a high thrust-to-weight ratio and some forward stick, the airplane did recover. However, now we were faced with what are we going to do about this characteristic? And so we thought about it. We were Navy fighter pilots. The airplane was going to be flown by Navy fighter pilots. So maybe this characteristic could just be handled by a note in ATOPS. And so we concocted this caution in saying that at minimum end airspeed, failure to place the stick forward at the optimum time will result in the loss of the airplane. We went to the fleet and we said, what do you think of this? And they said, yeah, that causes some concern for us. And so we added another sentence on there. We said, in addition to what we'd already stated, we said that, first of all, it will be spectacular. Secondly, the press release will say that you swerved at the last minute in order to avoid a populated area which included several schools. And third, you'll look good doing it. So right away, the fleet was very, very happy with that. Then we thought to ourselves, well, wait a minute, there's such a thing as exchange tours. So theoretically, we could have an Air Force pilot flying this airplane. So what are we going to do about that? And since this was all a timing thing, we just added another sentence that the timing can be facilitated by paying particular attention to synchronizing your wristwatches before you go flying. So as it turned out, we had to delete that approach, and what happened was they put a longitudinal stick positioner in the airplane, which didn't allow you to get the maximum capability out of the airplane, but it essentially gave you the ability of an airplane that had a trim capability, that you had predictable pitch rates off the boat, and then you could establish a viable minimum.
Well, those were the days. You know, it's very interesting when you take a look at the evolution of naval aviation after the Second World War, and you think about just how a couple of simple things relatively changed everything in terms of naval aviation safety. You think of the angled deck, you think of the mirror landing system, the problems that navies had at the end of the Second World War up toward the time of the Korean War, just integrating the turbojet airplane into the fleet. All these cause loss rates and accident rates that by the standards of today would be completely and totally unacceptable. And you take a look at the work of panelists in helping give us the naval aviation tool that we have today and the capabilities that we see naval aviation possess. And it really shows you something about the character of the work that was done and also the character and the detail of the technology. And this also depended, and we must remember this also depended on some very dedicated designers. You take a look at the designers of classic naval aircraft that we think of, the Ed Heinemans of the world, you know, the people of that sort, and also the civil servants that were right there. I think of people like George Spangenberg, for example. You had here remarkable individuals that really gave to us a remarkable capability that we certainly must remember in this centennial flight. Before we close this panel down, I'd ask first that we thank Kurt for his presentation. And I'd also like to throw it open to you for at least a couple of minutes for any of you that may have questions that you wish to ask of the panel. Come on, folks, it wasn't that good. Yes, sir.
Which engines were in the F-14?
Bob, it was they replaced the J-79 turbojets with Spey turbofan engines. So it really was the first attempt by anybody to put turbofan engines in a fighter. So they had more thrust than the J-79, and so in the carrier suit environment, that was very beneficial. It's an interesting thing happened, and it doesn't necessarily relate to carrier suit, but involving the F-4K program, the one thing that the airplane didn't do as well as the Navy version, and that was it wouldn't go as fast. And so when they went out to high Mach, it would not meet the specification. So I happened to be participating in a meeting between NavAir and McDonnell Douglas and the Navy regarding, and this subject came up about the max speed of the airplane. So they defined the problem, and so they turned to the manufacturers of the Spey engine, and they said, well, what do you think the problem is? And they said, well, clearly we're putting out the thrust. The must be drag on the airframe that's causing that. So they turned to McDonnell Douglas and they said, well, what do you think about it? They said, well, it's clearly they're not putting out the thrust. The drag on the airplane is fine. So they were at this impasse, and the meeting adjourned when they decided that the cause for it not going any faster was the airplane ran out of excess thrust.
This had an interesting little side effect, too, because eventually the Fleet Air Arm lost its large deck carriers. And, of course, the Royal Navy then eventually went toward a Harrier-based force and a helicopter-based force. And the classic Lake Naval Aviation aircraft that the Royal Navy had, aircraft like the F-4K and the Buccaneer, were then sent to the Royal Air Force. And in the case of the F-4K, integrating the F-4K into the RAF, together with the RAF, I guess was the F-4M that they had possessed, that caused some very interesting logistical and maintenance and training and operational problems for them as well. So nothing comes without a price. Again, I'd like to thank our panelists for their contributions. And we'll start organizing up here for the next panel on VSTOL flight. Gentlemen, thank you very much.